Hello and welcome to tonight's video for AP Calculus. Target 29. I can use the fundamental theorem of calculus to evaluate definite integrals. Well, why are we doing this? Yada, yada, yada. The fundamental theorem of calculus is the triumph of mathematical discovery and the key to solving many problems. That doesn't tell us why. That's crazy, this book talk. Basically, now we're going to be able to take this and instead of doing infinite rectangles, now we have the shortcut. So we don't have to do the limit as n approaches infinity of the summation from I equals 1 to n, yada, 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 1 over n. Now we can use the shortcut. And believe me, you're going to love this shortcut. It's way better than doing it the long way. All right, so basically where this shortcut comes from is we take and we look and we examine what does the derivative mean? Well, the derivative is slope. It's change in y over change in x. And as we do it as a derivative, it becomes dy dx. So the derivative relationship, or differentiation, is the division of the change in y over the change of x. Well, someone noticed that the integral relationship is the multiplication of the change in y times the change in x. So you're going backwards. Derivative and integration, they have a opposite relationship. And so they tied that together and said, well, hey, if I'm finding the area under the curve and it's the opposite of differentiation, why not integrate it? And so that's why we've been using the same symbol that we use for finding the area in the curve as we've been using for antiderivatives. So what we're going to be doing here, to find the area under the curve, we're going to integrate. So to find the area under the curve from a to b, you're going to take the antiderivative. And the antiderivative of f of x is big F. And we're going to evaluate that antiderivative at the limits. So we're going to find the antiderivative at the upper limit, antiderivative at the lower limit, and subtract the values, and that is our area under our curve. So if we kind of view this a little bit more in depth, right here, this is the condition that you can use the fundamental theorem. You can only use it if your function is continuous. In other words, you can't find the area of something that has a hole. And if there is an antiderivative, right? So use the fundamental theorem of calculus to find the antiderivative. Now notice this says part 2. Some books have this as part 1. There's 2 parts. We're going to get this other part later. I call this part 1 because it's basically where everything starts from. To find the area under the curve, you integrate and then substitute the values in. This is the integral evaluation theorem. All right? So to find area now, we're going to find the antiderivative, plug in the limits, and we got it. Now, to use the fundamental theorem, a couple things we need to do. First, in order to use it, this first thing, all that says is make sure you can use it. In other words, make sure there's an antiderivative that exists and make sure it's continuous. So make sure your function is continuous. Secondly, the second thing you'll do is you'll find your antiderivative, and then we'll plug in our b to our antiderivative, or upper limit, and we'll plug in our lower limit. And so, for instance, an example there, the area under the x cubed from 1 to 3. First we'll find the antiderivative of x cubed, that's power up to 4 and divide. Then you plug in 3, you plug in 1, and simplify. Go ahead, grab your graphing calculators and check that. Make sure that's right. You'll see that it is. And you'll also notice that we didn't do plus c. Plus c is only important if you have an indefinite integral. An indefinite integral does not have limits. Now when you have limits, you can still do the plus c, but as you do the plus c, you have a constant in both of those. And what happens when you subtract c minus c? Well, it's going to cancel it anyway. So when you're doing a definite integral, meaning it has limits, you don't need your constant. You only need constant if there's no limits and it's an indefinite integral. That, in conclusion, is how you use it. Now in class tomorrow, we will start practicing these problems. If you want to give them a try to see if you have it and then get the answers in class tomorrow, that's great. Otherwise, have a nice evening and I will see you in class tomorrow.